Welcome back. So let's continue with regression. And while we have a few more things to review or learn before we get to actual inference, you'll start to see some elements of it, okay? So first we need to talk about what residuals are, okay? Residual or error, and we're going to see these on a plot. So residuals are the errors in the model, okay? Now, remember, error doesn't mean anything, someone did anything wrong. It's just essentially variation. These residuals follow a t-distribution. Okay, so we're going to need this for our inference. The degrees of freedom are n-2, so we're subtracting 1 for the x and 1 for the y. Okay, so let's learn more about the residuals, and you may or may not be as familiar with these depending on the level of a regression that was done in your Stats 1 class. So residual is the observed value minus the predicted value, and it's just on the y, okay? So let me show you on our last graph. So on our last notes page, I had this line of best fit, which we will review also. But I have, let's just say for now, we've got this line of best fit. And how is that determined? How does the computer determine that this is the line of best fit and it isn't a little, less slanted or a little more slanted, right? Okay, so what it's doing is it's calculating the vertical distance from each of the points to the line, okay? I happen to have a little ruler here, so I'm going to try to get as vertical as possible. So you can see this dot has a short vertical distance to the line. This one over here has a lot higher, a lot bigger residual. Okay, and also a residual up here is positive, and a residual down here below the line is negative. Okay, above the line positive, below the line negative. It's a real handy way they set it up that way. Okay, so this residual, let me find one I can write on. So let me do this last one here. And that was the one before we said was kind of on the edge. So this is the residual. Okay, it's y minus y hat. And y hat is the point on the line. So it's observed minus predicted. Okay, so observed is the actual data point. Predicted is the model. The model is predicting. What the value would be. Okay, so we want to look at all these errors, all these residuals, and someone has figured out that they're distributed with a t-distribution. Okay, so that is what a residual is, and what we want to do is we want to look for even scatter in the residual scatter plot. So let's go back to Staplet first. We go down, here's a way, so we actually need to calculate the least squares regression line first, and so I'm going to hit that button. It gives you that line that goes through, okay, so this is the least squares of the residuals, this particular line, and we'll come back to that in a minute. And then here are the residuals again, but this line, instead of being curved, it's flattened out, or straight, sorry, instead of being angled, it's flattened out, okay? So it makes it a little bit easier, and you can see, like, okay, here's this, was this student, and then here's this residual, this student. So you can see how they're related to each other, but it makes the pattern a little easier to see when it's not on a slant, okay? So think of the regression line as zeroed out here as this horizontal line, and it just lets us see if there's any unusual patterns in the scatter plot. We don't want to see any patterns, okay? So let's go back to the notes for a second here. We want to look for even scatter in the residual scatter plot. No patterns, no variation in the spread, okay? So we don't want to see like the spread going from low to high or high to low. We don't want to see any kind of patterns in this, okay? And some programs will actually give you another one right here that shows a histogram of, so imagine these now are in a histogram here, they should follow a normal distribution, or we're using a t distribution. Okay, but they should follow a normal distribution. And so the residual dot plot, that's the next. So Staplet, instead of doing it on the side like some programs do, it has another graph for that. So if you're in Staplet, you can see that's the next one right below. So here it says residual against family income. So it's just the y, the residual is now the y value. And then the next one down says residual, and it's a dot plot. So if we narrow this up, then we would see it like the one I drew on the side right here. Okay, so this gives us an idea of the spread of the residuals. Okay, now you can also hide some of these if you want to, and we're getting down. We will talk about the equation in just a moment here. There's one other option, which is, where is it? Include more detailed regression output. Okay, so we'll look at this when we get into inference, but you can probably get an idea of, oh, we have a t value and a p value. Okay, I'll save that for just a moment. Let's go back to the notes for a second. Okay, so this is our residual dot plot. So essentially this is what this is, okay? Residual dot plot. And we want to look for normality in the residual distribution. Okay. Okay, great. So we've already kind of gotten to the model, so let's talk about it. So the least squares regression model. So it is a line, so it has the format of, you might be familiar with y equals mx plus b, but we just use different symbols in statistics. So we've got the equation. Since we're getting into inference, we're going to imagine we have a population regression line, right? Because we're trying to infer from this one sample back to the whole population of students at this college, right? So this is like mu versus x bar, right? So here's our population regression line is mu sub y is equal to alpha plus beta x, okay? And remember our the one without the x is the intercept, and the slope is the rate of change, so that's the one that's multiplied by the x. Okay, so we are doing a least squares estimate from the sample. And so I'll explain the least squares again in just a second, because that was pretty fast before. So this is from our sample, we get y hat equals a plus b x. Okay, same, a is the estimate from the intercept for the intercept, and b is the estimate for the slope. Okay, and you can see here's the output from Staplet. Y hat equals, if I put a comma here, I can get 24,319 and change minus 0.04307x. Okay, you can also see that we did indeed have 50 data points, and we have an S. Okay, so we have a standard, I gotta think for a second. This is standard error or standard deviation. We have an S, and then we have R squared. Okay, so we haven't talked about R squared yet. We'll do that as well. Okay, so what does this least squares estimate mean? And remember, you can look at more at the Stats 1 videos for more on this. But when we talked about the residual, then some are positive, some are negative. So then they're squaring them all, adding them up, and the best fit line is the one that has that smallest sum. Okay, so you can imagine if you had a line really far away, you'd have really big residuals, and then those would be squared, added up, and you'd get a very large number. The best line has the smallest sum of the squares. Okay, so least squares regression line. If you see least squares regression line and just regression line, it means the same thing. Okay, least squares just tells us how that's being calculated. Okay, so let's talk a little bit more about the slope and interpret the slope. So slope is rise over run, which you might remember from algebra. And we can also draw that on the graph. So slope, if I go between 2 points on the line, I have to go up or down or over, right? So this would be down and over. So the rise is the positive or negative up down part, and the run is the horizontal part. I don't have a lot of room to write right there, so maybe you can find a better spot to put it. So the vertical part is the rise, the horizontal part is the run, right? So this is a measure of how steep the line is, how steep the relationship is. Okay, so it's a measure of steepness. Also tells us whether it's positive or negative, okay? So let's interpret the slope. For the Elmhurst data, what's the sample slope, intercept, and standard deviation of the residuals? What do they mean? Okay, so let's go ahead and work on that. So let's work on the slope first. So slope is rise, which is a change in the y, that's the vertical, and over run, which is the change in x, or horizontal. So to do this, it's really, really important to add your units in so you can get the right units on your slope. So what I'm going to do is write the actual slope right here. So negative, and it's in dollars because we're talking money. The slope is the one with the x, negative 0.043. Negative 0.043. I'm just going to keep it to 4. Actually, they went out 5 to 0.431. In aid. Okay, so this is dollars in aid. It's less than $1. So this is really cents in aid. Over, we're going to put 1. We're always going to use 1 for the denominator. You know, you might have seen nicer slopes like 1/2, 3/4, or you go up 3/4. But we're always going to have some kind of decimal here in statistics. So you can make any number into a fraction by putting that number over 1. So if we take this value in aid, the slope value, over 1, but now we need to do the units of the x, right? So still dollars. Here they're both dollars, but they won't always be the same units. You know, it could be miles per hour, miles per gallon. Those are all rate units. $1, the x is the family income. Okay, so this really helps us interpret the slope. Now, another interesting thing here is, I mentioned earlier, we could rescale this. We could scale this differently. So let's say we don't want to just do like for every $1 increase in income, because that's makes it sound a little more precise than it actually is. What if we multiplied both of these by 1,000? So I'm going to rescale this. And to do that, that's going to move the decimal over 3 zeros, so it should be 3 places, but I'm just going to do it to make sure I don't make a mistake. Put it over here. 0.0431 times 1,000. Yeah, 43.1. So 1, 2, 3 places. Yeah, so the number of zeros is the number of places it moves over, just like 2 for 100 and percentages. So still dollars, but now it's 43 10 or 0. Now I'm regretting rounding that to 1 because it would be 43.07 in aid over, and now 1 times 1,000 is going to be 1,000 in income. Okay, so this would be a choice you would need to make if you were interpreting and explaining, describing this data set. Does it make sense to talk about every $1 increase in income, or every $1,000 increase in income, or some other, 10,000, some other measure like that? To me, I think it makes more sense to talk about the thousands, because it's not quite, everything in statistics is an estimate, so it's not like exactly 4 cents less aid for every $1 in income. I think 1,000 gives us a little more sense that it's an estimate. Okay, so let's use this to write out our slope first, and then we'll come back and talk about intercept and more about the standard deviation of the results. Okay, Okay, right. And this is standard deviation because it's one sample. It's individual to individual variation shown in the residuals, not sample to sample variation. Okay. All right, so for the Elmhurst data, what's the sample slope intercept? Okay, and what do they mean? So I'm going to do these one by one. So slope, and what does it mean? So I'm going to say the estimate, because we're estimating the population slope, the actual slope, with our sample slope. The estimate for the slope is, you know what, I forgot my negative sign up there, so I'm going to add it in right now. Negative 43.07. And, you know, so I have rescaled this. So I'm just going to put over 1,000 to show that I've rescaled that instead of over 1. If I didn't rescale it, I could just give that decimal right there, but I don't want to be confusing. And then we'll explain it more. So this means for each additional 1,000 a family earns in income, the aid award is reduced by, and reduced is my negative sign, reduced by $43.07. Okay, now I could say about, but I've already got estimate right there. Okay, but we know this is very approximate, and there's error built in because of variation built into this. Okay. Okay, so remember, the slope is just how you get from one point to another. It's not the starting point. So the intercept next is going to be our starting point. But that's why we say for each additional 1,000 a family earns an income, based on some starting point, the aid award is reduced by that much. Okay, now the intercept, let's go back to our graph. The intercept is where the line intersects with the y-axis. Okay, so I've got the x-axis, the y-axis. This value, you can think of it as like a starting value. So this is our y-intercept. Sometimes it makes sense as like a baseline. Sometimes it, and actually this, you have to look at the scale very carefully. This is 0, so it's actually right here. Be careful about that. So just get rid of that point right there. It is at the 0 line, okay? So also keep in mind your graph, because maybe we're talking about years and it's 2025 or whatever year it is now. So maybe this is 2025, but remember the y-intercept is year 0. So it doesn't always have much meaning to it. Like we can't go all the way back to year 0. Things were way, way different back then. So they don't always make sense in our interpretation, but we need to look at that and see if it does make sense. Okay, so our intercept is this 24,319.33. Okay, I did rescale all this data, but I think I didn't rescale the data. I rescaled the slope. So the starting point still stays the same. So I'm not going to adjust that value. And this is in dollars as well, dollars of aid. So think of this as if a family had $0 in income, this would be the award they would get. Okay. Don't know if it's possible to live like that, but I imagine it's possible for that to happen. So the estimate for the y-intercept we could say, okay, this is the baseline award. This is the lowest award amount, or sorry, the highest award amount given, because it's going down from there. The estimate for the y-intercept is 24,319.33. $4,000, $319.33. And also we could just put that into dollars since it's all an estimate anyways. This, to explain what this means, this is the amount awarded if a family's income is $0. Okay. Also, I might want to just put in the average. Okay. Okay, and then I'll just make a note. The intercept is not always meaningful. Okay, so depending on your situation, you could state what it is and then say this is not meaningful, or it might make more sense to leave it out. So decisions you have to make in statistics. Okay, now let's get to our last one of standard deviation of the residuals. Okay, what do they mean? Okay, so this is our S value right here, and they're talking about the residuals of the residuals. Okay, so you could think of this as residual to residual variation, or individual to individual variation of the residuals. Okay, and let's go back here. Remember how I talked about we're looking for normality in the residual distribution? Here's our dot plot, and so think of this S, it's a 4,800, okay, a little less than 5,000. So if I look on this scale, 0 to, let's say 5,000 is right here, so 48 just right about here. This would be from 0 to that would be 1 standard deviation of the residuals, right? And then a little less than 10, that would be 2 standard deviations. And then be a little less than 15,000, so it doesn't go past 3, which is great. 3 standard deviations, okay? Just to help get that context of we're looking at like this to see if the residuals follow a normal distribution. Okay, so that's what that S means, that standard deviation means. It's hard to switch to standard deviation because we've been talking about standard error so much. Okay, the standard deviation of the residuals is, and remember it has the same units as the data, 4,782.598, so 6.60 cents. What does this mean? This is the average deviation. And we're talking about the y values from the regression line because that's what the residuals are. So average deviation of the residuals, but what does that mean? Average deviation of the y values, or of the aid award from the regression line. Okay, so this matches up with what does standard deviation mean in Stats 1? It's the average deviation from the mean, right? So think of the regression line as kind of like the mean. It's the average. It's kind of an average. And so we're talking about the average deviation of the y values, or the aid awards, from average, or from the regression line, okay? Okay, great. Well, let's keep going. I'll see you in the next video.